Good afternoon, everybody, and welcome to the Distinguished Lecture Series of the Institute of Applied Computational Science. Today, we have a distinguished member of the Harvard community, Professor Susan Murphy. Professor Murphy is the Mallinckrodt Professor of Statistics and of Computer Science, and she's also a Radcliffe Alumni Professor at the Radcliffe Institute at Harvard University. The lab of Professor Murphy is the Statistical Reinforcement Learning Lab, and their work is concerned with the development of data analytic algorithms and methods for informing sequential decision-making in health and for developing personalized digital health interventions. They have been doing some great work in developing clinical trial designs and data analysis to inform the development of just-in-time adaptive interventions in digital health. And Susan has developed the micro-randomized trial for use in constructing digital health interventions. And this trial design is in use across a broad range of health-related areas. Susan is the 2013 MacArthur Fellow, and at the same time, a member of both US National Academies, the National Academy of Sciences, and the National Academy of Medicine. We are grateful, Susan, that you take the time to present to the seminar today, and we're looking forward to your talk. Thank you.
Thanks, Petros. I'm going to share my screen.
Please.
And now I have to fix the pictures so I can see. Okay, great. So you can see on the screen, I have little icons for a variety of projects that we've been involved in. These are all projects in digital health, and they all involve sequential decision-making, how to learn how to when to send messages, what kind of support to send, when and in what places, and so on. Today, we're going to spend our time on one particular trial, or actually two trials, but they're part of this HEART steps. This is a physical activity trial. This type of work, it requires a big team. Pedja Klaschner, he works in human-computer interactions. There's behavioral scientists on this team. There's app developers, software engineers. Peng Liao was a postdoc in statistics here. Kelly Zhang is a PhD student in computer science here at IACS. Zheyang Ji is a PhD student in statistics. So what I'm going to do is I'm going to start off with a description of this study. It's going to help me make things concrete. So HEART Steps is a series of 3 experiments, 3 trials. And the idea here is to develop a mobile activity, physical activity coach for people who are at high risk coronary artery disease, in particular people who've just been diagnosed with stage 1 hypertension. We're going to spend our time on the second 2 studies, the 3-month, that is the 90-day study, and the 9-month study, the 270-day study. You can see the adjectives for these studies. They're called micro-randomized studies. And then there's another adjective, personalized. And I'm going to try and make that clear as we go through the next couple of slides. So in HEART Steps, it's like most apps. There's a whole variety of intervention components. There's 6 in this particular case, and we're going to only focus on one of these components. And this has to do with these contextually tailored physical activity suggestions. These can be delivered at any of 5 times. The times are related to the way the individual lives their life. So that person's version of morning, that person's version of midday, and so on. They're about 2 to 2.5 hours apart. And so at these times, that individual could get a contextually tailored message. And you can see an example of one such suggestion. This came to me on a work day. So it is tailored to the time of day, where I am at that time, the weather outside, and weekend versus weekday. And it was pretty cold that day. It's tailored to the weather, trying to get me to think, reframe it, and go for a walk despite the fact that it was cold. It was in the morning on a work day. And we're going to focus here on whether or not one should deliver such a message. And the way the messages are delivered is your phone screen lights up, and then there's a notification. Also, there's an audible sound. So when I say micro-randomized, what I mean here is that this treatment action, deliver versus do not deliver, is randomized. That's 5 times a day it's randomized. And so depending on the study, say in the 9-month study, we're talking about over 1,000 randomizations per person. These messages are supposed to help the person in the near time, where they are with the current weather. And so the goal here, when you think of the reward or the outcome, it's a very near time outcome. And in particular here, it's the subsequent 30-minute step count. So the thought was that delivering a message would lead to a higher step count than not delivering a message. After a trial like this, in which you've randomized deliver versus not deliver at each of those 5 times, the data has this structure. On each individual, you have a time series of tuples: S state, A action, R reward. The state here is it's a variety. It's sensor data collected by the phone, how busy the individual's Google Calendar is, for example, around that time. It's also data collected by a wristband tracker. And there is, sometimes there is some self-report. In these particular studies, there wasn't self-report, but often there is in the state. And then A is the action. In our case, we're gonna just look deliver versus not deliver. If the suggestion is delivered, it's always tailored to the current sensor data. And the reward is that near time outcome that I mentioned on the last slide. Here, we're going to take the log, and we do that because 30-minute step counts are highly skewed, and a lot of approximations work better if you have a more symmetric variable. So log of 30-minute is much more symmetric than a 30-minute step count. At the bottom of the slide, you see some notation that I'm just going to return to over and over again. And that's the notation for the expected mean of the reward. In the case of hard steps, the log 30-minute step count, given the current state S and the current action A. And so we'll use lowercase r S A to denote that conditional reward, given state and action. So what we ran in this study, it wasn't exactly a Bandit. It was partially, it was between a Bandit and a full RL algorithm. So during the study, what this algorithm does is it attempts to maximize the sum of the rewards, but that's subject to a variety of constraints. And at the time we were designing this algorithm, we only expressed the constraints in a very ill-posed way, a very qualitative way. We wanted to ensure that after the study was over, we could conduct a variety of causal inferences. We wanted to ensure that we could do off-policy learning after the study was over. We were also, another sort of ill-posed or not qualitative constraint is we know that there's issues with habituation. If we send too many suggestions within a short period of time, people don't even see them. So we have to manage that somehow. So the message here is that all of these constraints imply that even though we want to reduce the regret, we want to make the best, we want to choose actions which maximize the rewards. We're not going to target regret minimization. And indeed, in all of our studies, we are in this setting. We don't target regret minimization because of these types of constraints. And in Hard Steps V2, the 3-month and the the 9-month study V3, we generalized a Thompson sampling algorithm to choose the actions during the study. And I'll talk to you just briefly about that. That's not the main topic today, but I'll just give you a feeling for what we did. So there's two elements to these algorithms. If you look at it, particularly from a statistical point of view, these elements come straight, they're immediately there. The first element is a learning algorithm that incrementally updates some model. And in the case here, it's going to be a model of that expected reward given state and action. And the model we used in this study was a Bayesian linear regression model. So it's a very simple GP model for the reward as a function of state and action. That's really nice. The Bayesian paradigm makes a lot of sense in this setting because it provides a natural way to update the model as data accrues on each user as time progresses. The other element of these algorithms is how the actions are selected. And in particular here, because we're using a Bayesian algorithm, learning algorithm, it's really natural then to use posterior sampling. And so in posterior sampling, what one does is you calculate the posterior the posterior probability that one action, say action 1, is better than action 0. You calculate that posterior probability, and then you use that probability, the resulting probability, to randomize. So you are randomizing, you're just randomizing with this posterior probability. And in particular, with this algorithm, the one we ran, we looked at the posterior probability that the reward, the expected reward in state S, if you sent a suggestion, minus the expected reward in state S, if you didn't send a suggestion, if that difference is greater than some threshold. And this threshold we constructed with Hartstepp's V1. I'm not going to spend much time on this, but if you're familiar with RL, you can imagine we actually used a Markov decision process to construct that threshold. But in the conduct of the trial, this current trial, we did very little updating of that threshold. And in fact, in the Bayesian paradigm, we didn't incorporate the uncertainty in that threshold. We just took it as given. So we calculate the posterior probability that sending a suggestion is better than minus not sending a suggestion, the reward, if you send a suggestion, minus the reward if you don't send a suggestion, if that difference is greater than a threshold. That probability will be really high if the accruing data indicates that it's good to send a suggestion. And vice versa, it'll be very low if the accruing data indicates that it's not good to send a suggestion. That's what we mean by personalization here. So personalization here means the chance of the individual getting a suggestion in a particular state depends on how the accruing data, and as that accruing data indicates that it's good to send the suggestion, then with higher probability the suggestion is sent. So as I said, we used the learning algorithm. So this is just one point about the learning algorithm. It uses a Bayesian linear model. And in particular, what we do is we have a linear model for the advantage of sending a suggestion in state S. That's what this difference is. It's the advantage over not sending a suggestion. And we have a linear, and F, the vector of features is only 5-dimensional. And you'll see the names of these features shortly. The first feature is just an intercept. It's just a bias term, and that's going to be important. I'll talk about that, talk why that is the case shortly. So by using a very simple model, we're essentially trading bias and variance. It's going to be much easier to learn this linear approximation for the advantage of sending a suggestion versus not in state S. We also used, because we were so concerned about noise, we used an informative prior. We built our prior based on the prior study, Hartstepp's V1. So it was this is a Thompson sampling time paradigm. So it's a Gaussian prior. And so it's the prior mean and the prior variance that we really constructed. And the prior mean for that first term, the first value of theta, so theta is 5-dimensional, the very first value of theta, the prior mean is positive. And that mean is associated with the overall effect of sending a suggestion versus not. This is going to become important as we go through. All of the other prior means were 0. The prior variance covariance matrix also came from that original trial, the Hard Steps V1 study. So this is another way for us to warm start the algorithm to better manage the noise that occurs in this kind of data. So I've given you 2 ways that we manage the noise. We use a relatively simple model for the advantage of sending a suggestion versus not. That's the first bullet point. And the second bullet point is we use an informative prior. Then in the action selection strategy, this is how the actions deliver a suggestion versus not in the case of Hard Steps, how they're determined. And remember, we're using posterior sampling. So we calculate this posterior, the algorithm calculates this posterior probability of this advantage in state S being greater than the threshold that was built on prior data. And at first I didn't realize these kinds of things. We actually ran a pilot study. And this is when I realized the points I'm going to bring up next. And we changed the algorithm as a result. Okay, so in some states, the Gaussian the posterior distribution of the Gaussian, it's going of the advantage minus the threshold. That posterior distribution is going to be centered at 0, around 0. So what happens to your posterior probability? Its averages around 0.5. So here we are in a setting in which the accruing data does not give us much evidence that it's good to send a suggestion in this current state. And what are we going to do? Send the suggestion with probability 0.5. Does this make sense? No. In other states, the posterior distribution of the advantage minus the threshold will be centered at a value much greater than 0, and it'll be peaked. And then what posterior sampling is going to want to do is it's going to want to have a very high posterior probability. They'll send a suggestion with very high probability in that state. That's another issue. Is that a good idea to do? Remember, I already mentioned that if we send too many suggestions within a short period of time, we're likely to get habituation. People won't even see the suggestions. A third point is we must, because these are large interdisciplinary teams and each member of the team has to be able to, we want to be able to inform the behavioral sciences. We have to permit off-policy learning after data collection ceases. We want to permit a variety of causal inference analyses. So how do we deal with all of this? First of all, we definitely do not want to send the message with probability 0.5 if there's no evidence the message works. So you can see I drew a little figure by hand here. The the x-axis has the posterior probability, and the y-axis has the probability the software actually ends up using, the algorithm uses. So when the posterior probability is around 0.5, we threshold it to 0.2. So 20% of the time a suggestion would be sent. If the posterior probability was 0.8 or higher, it got set to 0.8. And the last 2 sentences on the slide tell you what our considerations were. This upper bound 0.8 and the lower bound 0.2, these numbers were determined by the whole team, including the behavioral scientists. And the idea here is 0.2 is what fraction of the time do we want to send this suggestion when the current data indicates the suggestion might not be helpful. And the team decided, well, we'll do this 20% of the time. So that's how the lower bound got determined. Of course, having a lower bound of 0.2 and an upper bound of 0.8 for these randomization probabilities really facilitates off-policy learning after the data collection is over, which is great. Okay, I'm supposed to pause for a clarifying question. Petros, did we get any questions, or should I go on?
There is one question here from Ian, Ian Kwa. Ian, would you like to turn on video or maybe just voice your question?
Hi there. Would you mind going back to slide 8?
Slide. Okay.
Thank you.
There we are.
Okay, so facilitate off-policy learning / causal inference after data collection ceases. So by this, do you mean that you collected the data, trained it, and then trained a model on that data and then deployed live?
This is all live. All of this is live. This algorithm was running during this trial. This algorithm was running in the cloud, and what it would do is we had this whole API built. So it would send decisions to the API, you know, it was an API, send decisions to the phone. This is all live.
I see. Okay, so the causal inference was after the data collection ceases, and I see. I got it confused. Okay, thank you.
That's great. Thanks for the question. Yeah, in fact, like if we allowed the algorithm to get a probability too close to 1, for example, in certain states, then in those states, the algorithm would pretty much always send a suggestion. And then in after study analyses, we'd never be able to learn if it was better not to send the suggestion. So that's the reason why we do this.
Mm-hmm.
There is one more question by Misha. Misha has about 4 questions, but maybe Misha, you can choose one of those and pose it, and then leave the others for later. Misha Kazakin, if you like to. Yeah.
Hi, sorry. Yeah, it's hard to choose one.
I can choose for you.
But I think that my main question would be, like, based on my experience with notifications on the phone and, like using habit forming apps, there might be certain adverse reaction to notifications that are perceived as irritating, like, bad timing. I don't want to be told what to do. Actually, kind of, I want it to be better, but something tells me what to do. Kind of, it's like may cause some adverse reaction, like lazy to walk today, or like feel guilty about it, about like not doing it, and then when I see a next notification, actually. So what's the kind of, did you design like UX to help reduce that? Like, because I think that that's sort of, that is a part of the problem. Like, how to say, you cannot really, like, your reward, negative reward or like positive reward, even if you do like reinforcement learning, can be affected by this like dynamic, like dynamic psychological, I would say, like hidden state for the user.
Yeah, you're totally right. This is exactly the kind of issues that we talk about all the time. So we were really worried about burden and habituation. So burden is exactly what you were saying, and habituation means that I may be engaged, but I just don't see the signal anymore because I had too many repeated stimuli. That's a common thing that happens. It's been well known back to Skinner, for example. There's a human computer interaction guy who's part of the team. So the UI is really a big deal. How you collect the data, if you get any self-report, is really a big deal. How you get buy-in from the individuals is really a big deal. Each one of these studies incorporates user studies prior to it, and often we have qualitative studies after. That's one of the reasons why it requires such a big team, is so many people have to come together. The other thing I want to say, though, is when you go to industry's done a great job with placing ads on Facebook and Google and something, but they haven't done the best job with mobile apps in terms of not providing they ping us continuously, and this just hasn't gotten very far in industry. So thanks for the question. Okay, I'm going to go on. So during this trial, as we just spoke about, this algorithm was run, and it's sort of a halfway between a Bandit and a full RL, because remember there was that threshold which was intended to account for delayed effects of the actions. And it was run separately on each user. There was 91 users, and the algorithm is run separately on each one. In the trial, it was run separately on each one. And our lab's done a variety. We've done work on how you can assess effects, population level effects after you've done this sort of thing. I'm not going to focus on that here. What I'm going to do for the purposes of the rest of the talk is I'm going to act as if we have a Bandit environment. So what I mean by that is on each user, remember these suggestions, they can occur only around 2.5 hours apart. So it turns out the data, there's very little correlation between the activity 2.5 hours apart. And so we're going to act as if our environment, each of those tuples, state, action, reward, it's like a little IID kinds of tuples. Of course, the actions aren't, because the actions are being made by the algorithm, and the algorithm uses all the prior data on that individual. But to address these questions, this is the environment we're going to assume. As I said, we have methods for doing this when we don't make that assumption, but I want to do that here. So this is how I'm going to proceed. So the first question I'm going to ask, I'm just trying to get at, did we personalize really? And I want to use this environment as a way to think about it. I'm going to ask, is there an effect of sending a suggestion versus not overall? Is there some evidence overall across all people? And then I want to ask, is there a lot of treatment effect heterogeneity? Do you really have evidence of treatment effect heterogeneity? And as I said, I'm going to assume we have a more classical Bandit environment. So if I do this, when we were first thinking about this, we were pretty stuck, because there isn't much in the literature about how you think about the performance of these algorithms once they've been run. And what we ended up doing was we ended up using this really old idea called meta-analysis. This is not meta-learning. It's the meta-analysis idea comes out of classical clinical trials, and it's used to this day to combine data from multiple clinical trials of the same treatments. It's used across the world by the main regulatory agencies. And what we're going to do is we're going to use those ideas here. So to do that, I'm going to act as each user is a clinical trial, and each user has capital T tuples. It depends on if they're in V2, the number of tuples only comes from the 3 months, and if they're in V3, the number of tuples comes from 9 months. So each user has her own number of tuples, and there's a whole bunch of tuples per user. So each user is akin to a trial. Each user, I remember I said that we parameterize the advantage of sending a suggestion versus not by a 5-dimensional feature. So with the weights, the theta are the weights. So each user has their own unknown true weights for that feature, for those features. It's 5-dimensional. And we're going to estimate those weights using each user's data. So if you look at the user level, you realize that this Bandit algorithm, all it's really doing is doing L2 penalized least squares. So this theta hat I for the ith user is a weight that's determined from least squares with L2 regularization, often called ridge regression. So how does this fit in classical meta-analysis? Again, each user is a clinical trial. And in this, this meta-analysis is very, very mature area of science. In fact, the paper that's cited at the bottom of that slide, that was written when the field was pretty mature in 1999. And it's a beautiful paper. And we're going to use the methods from that paper, but we're going to we're going to, in our mind, we're going to think each user has their own vector of weights, and we're going to estimate that vector of weights at the user level. That's theta hat I is our estimate of the weights. And that just comes from this L2 penalized least squares. So in meta-analysis, there's two ways that you think about inference, classical meta-analysis. One way is you say, I'm only interested in these trials, that is these 91 users. You can only make inference about them. And the assumption there is this least squares estimator with the L2 penalization. Its distribution at the user level can be approximated by a normal. A normal with that unknown, the mean is the unknown vector of true weights for that ith person, ith user, and some variance covariance matrix. Okay. And the second way to think is population level inference. Now, instead of thinking you're really interested specifically in these 91 users, you're interested in a bigger population of users. And the 91 users is a sample from that bigger population. It turns out that makes a lot of sense with heart steps, because the way heart steps, this trial was conducted, the trial was conducted at Kaiser in Seattle. And what they did was all of the patients, when they got diagnosed with stage 1 hypertension, they were asked, would you like to join this trial? So it was so the big population, the population would be patients at Kaiser who were newly diagnosed with stage 1 hypertension. That's the target group, target population. So in this case, you think of a hierarchical kind of model. Now, each user's vector of true unknown weights, that's theta 0I, that has a normal distribution across users. And so there's some overall average across the whole population, 5-dimensional vector for each one of the features, the 5 features, and then a variance covariance matrix. So this variance covariance matrix here is between user variance, and this variance covariance matrix is within user across state action reward tuples. So here I am using these classical methods, and I'm going to address those questions I posed to you. So the first question is there any evidence of an overall effect of the average treatment? I'm going to do this at the population level. So I'm interested in all patients at Kaiser who just got diagnosed with stage 1 hypertension. And I'm going to show you the statistic. So this test statistic, E is a one-hot vector. It's just used to pick out each one of the 5 features. You can see the list of 5 features in the green table. Each row corresponds to a feature. And the test statistic is just a weighted average of the different thetas. So the theta I. So there's a weight, the ith weight for the ith user, and then it's that user's feature weight for whatever feature is being picked out, say like the feature that corresponds to the first row in the green table. And the weight has to do with the amount of uncertainty associated with that estimator of that theta I, the uncertainty in theta hat I. Okay, from that one can do, this is all classical statistics summarized in 1999. And you can write down a confidence interval. You get your estimator, you have a confidence interval. And that's what's in that table, that green table. So this is on average across all users. So every user has his or her, their own Bandit algorithm. Now we're looking across all the users. And you can see the first weight is positive. The confidence interval doesn't contain 0. It corresponds to about an increase in 50 steps, sending a suggestion versus not, over a baseline rate of around 250 steps in 30 minutes. It's a nice effect. It seems like it's a nice effect until you look at the second row. Then the second row has to do with how many times has that user received a suggestion recently over the last day. And that prior dosage is standardized. What you immediately realize is as soon as that prior dosage is sort of positive, that's going to kill the effect of the suggestion. of sending a suggestion versus not, because that weight is negative. And its confidence interval is also completely negative. These are the only two rows in which there's anything really worth saying, according to this data. This is very depressing, at least across the population. It seems like if someone has had any reasonable amount of suggestions recently, they're much less likely. On average, across all people, there's much less likely to be an effect. Okay, so now we go to, I want to bring this home, this effect of the dosage. So I'm just going to look in one particular state. And the state that I'm going to look at is the state of, they've had their recent dosages about average, the average dose of suggestions. They're currently engaged in the app. That means they've been looking at the app of their own volition. You can go to the app and you can track your behavior. You can do all kinds of things on the app. So they've been doing this of their own volition. They're currently, at that time, they're in a structured environment. That means they're at home or work. And they haven't been that active around that time in the prior week. So I'm focusing just on that one state. And you see the effect, the estimated effect at the bottom, 0.1, and the confidence interval contains 0. And that's really due to this negative, the negative effect of having been sent a lot of suggestions, and even an average number of suggestions. Okay, so this is all on average across everyone. So what happens when you start to think at the user level? So the next question is the better action user specific? You know, some people are really responsive in certain states, other people are not, and so on. And we're only going to be interested in these 91 users. So if we use the ideas from meta-analysis, here's how we combine the results across users. So each user has their own theta hat I. And remember, E is a one hot vector. It's just picking out which of the 5 features we're focusing on it. And we subtract from it the overall average across all the users. You see the formula for the overall average at the bottom of the slide. It's weighted by the amount of variation that's associated with that estimator theta hat I. And then we square that difference and we weight it again. This is in statistics, this is a chi-squared statistic. There's 91 users. This statistic has 90 degrees of freedom. So when you go to make a confidence interval or conduct a hypothesis test, you use a chi-squared on 90 degrees of freedom. So that's what we're going to see on the next slide. So the null hypothesis is that all of our users, our 91 users, their theta weights are all the same. Their true unknown theta weights are all the same. And you see each of the rows. Lots of evidence that this is not the case. There's lots of evidence that there's treatment effect heterogeneity. A great deal of evidence. So now I'm going to ask these questions in another way, more classical reinforcement learning way. On average, does the Bandit algorithm select more effective actions than the prior? So this question is a more composite question because this question depends also on the states that that individual was in. It's not just on the effect of the action, it's also what state. So if a person was always in adversarial states or states in which the effect is not very big, that person's not going to benefit very much. So, but still we're going to look at average across people. So what we're looking at now is the average reward for a particular policy. So the policy, remember policies, input state and output action, and these are stochastic policies. So they'll output the probability of an action. So that's the value of the policy pi, and it's indexed by I because it's at the user level. This is just the expectation of the reward over at state S under policy pi. And that expectation is averaging over the state distribution for that ith user. And it's also averaging over the fact that our policy is a stochastic policy because we're using posterior sampling. So how am I going to look at this? Well, what I'm particularly interested in is the effect of the Bandit relative to the prior. And why? Because the prior gives me a policy we could have saved a lot of software engineering time, a lot of heartache, if we had just made up a policy from the prior and used that policy to choose actions during the entire duration of the study. We didn't have to use an online algorithm. So when I want to compare the expected sum total reward, I'd like to compare it under the Bandit algorithm versus the prior policy. And so what you see here is two off policy. I see you, Jackie. I see these are off policy estimators. Well, the first is on policy and the second is off policy. It's a pretty primitive off policy estimator. There's better ones, but we'll use this one here. And now we'll make the same type of, we'll use the meta-analysis approach, but now theta is just one-dimensional because the value function is just one-dimensional. I want to get to this slide. So, but here's the results. On average, if you compare the policy, the learning algorithm, so this is like a learning policy, versus the prior policy, the estimate of the advantage of the learning policy is 0.05. This corresponds to about 19 more steps in a 30-minute step point. And there's a confidence interval. And we believe this is mainly due to the fact that the prior had a positive weight on the overall effect of sending a suggestion versus not. Remember, the prior mean had that positive weight on that first component of the theta vector. And then when we look to see if the benefit appears variable from one user to another across the 91 users, gross evidence that there's enormous treatment effect heterogeneity. So sometimes this learning policy appears to be highly beneficial, and other time for some users, and for others of the 91, it doesn't seem to be very much. Gross differences in effect. Very interesting. So these are the analyses that really actually motivated this whole study. The one that really motivated is the question 7. But to help you understand question 7, I have to do question 6. And question 6 is, on average across users, did the Bandit algorithm pick up the fact that the prior was wrong? The prior, remember, the prior put a positive mean weight on the overall effect of the action. And it put prior mean weights on all the other features. A prior zero weights on all the other features, but a positive weight on the overall effect. Does the Bandit learn this on average across people very fast? Okay, so this blue curve, so let's focus on the figure on the left-hand side. So the blue curve you see, and I think you should be able to see it better than I can. The blue curve, it starts, all these curves start at 0.47 because that was the prior mean of the effect of sending a suggestion versus not. The blue curve, and the blue curve is real data, the real data from the real study. And it's the average posterior mean of the treatment effect in state S. And the state S is given to you in the second bullet point on this slide. So you can see that blue curve starts off high because the prior said it was going to be positive. And then it deteriorates and goes down to 0 as day in the study progressed. Is that very fast? How much of that is just due to this is a stochastic algorithm. It could be due to noise. So that's what the black curves are about. There's 2,000 black curves. Each black curve was constructed under the ground truth that there's no prior treatment effect. You still start with this prior distribution, but the reality, the ground truth is that the prior treatment effect is in fact true. Forgive me. So all 2,000 curves are constructed under the scenario that the prior is correct. The way each one of those curves is constructed is we took each of the tuples for each person, we stripped away the reward signal, and we ended up with state residual for that person across time. Then we ran the Bandit algorithm again on that individual. If they didn't get a message, we left the residual alone. If they get a message, we use the prior treatment effect to give the signal for getting that message. So, and then each curve is the average across 91 bootstrapped users. So that is, select 91 users from this set of the original 91 users and create the black curve. But each black curve, again, is under the ground truth that the prior mean policy is correct. Now you see that the data in the trial indicated pretty quickly that the prior is wrong. In fact, if you look at the bottom, you can see that blue curve starts to get below all the black curves around a month. So within a month, on average across people, the algorithm, the Bandit algorithm has figured out, look, that prior is wrong. We shouldn't use the prior. It's really nice. The figure on the right-hand side is, it's to make sure we knew what we were doing. Here, all the black curves are constructed under the ground truth that the posterior mean is correct. And you see there, the blue curve stays well within the mass of black curves. Okay, I just want to show you the one more analysis. This is about, and this is really disturbing. We had a number of users that looked really interesting. And the question is this spurious? So here's one such user. Remember, this is in Seattle. The person came into the study in November 15th, 2 years ago, 2019. And they left the study in August, early August 2020. So you can even see the period of time when Seattle shut down due to COVID. That's around this March, this late March period. The y-axis is the treatment effect, the estimated treatment effect in the user's current state divided by the estimated standard deviation in that user's. So it's a posterior treatment effect divided by the posterior standard deviation in that user's current state. So if it's high, that means with high probability they're sent a suggestion. If it's low, that means with very low probability they're sent a suggestion. We color-coded those dots. The blue dots correspond to a state in which the user was currently engaged. The red dots correspond to a states in which the user was much less engaged. It's glorious. I see a graph like this and I want to put it in all my grant applications, because this is like personalization. This algorithm is great. I should be allowed to do all algorithms on all mobile devices, right? This is what I think to myself. I'm just in cloud 9. But is this true? This was a stochastic algorithm. Is it really true that the blue dots being higher than the red dots, is there really a signal here? Is it true that we're learning that in the engaged states, the user is more responsive? So here's, again, the blue curve is the real data. It's the posterior mean for the interaction effect of engagement on treatment. Each of the black curves is a bootstrap version of this user, but calculated under the ground truth of no effect of engagement. Now, the prior on engagement was 0. So that's why all the curves start at 0. You can see at the far left, all the curves start at 0. What do you see? That blue curve stays well within the mass of all the black curves, well within the mass to probably June of 2020. So only by then is there some evidence that the treatment effect is deviating from what could have happened if there were no effect at all. So if there were no effect of engagement, all the black curves are under that scenario. And only later in the study does the blue curve provide enough evidence that it differentiates itself from all the black curves. Yet if I'd gone back, I would look at this and think, oh, wow, in December 2019, we already know that it's better to send a message when they're engaged. But the stochasticity of the algorithm, there could have been no effect, and the person could have been anywhere in this black curve mass. And this is my last slide. We used a sequential decision-making algorithm to personalize. But did we achieve personalized digital health? To try and address that question, we acted as if each user is follows a classical Bandit environment. How would you do if you're willing to accept that assumption? How could you do a better job? I'm positive there has to be a way to do a better job. This is the first time I've seen an effort. More importantly for me is how to address whether or not your algorithm did a good job if the Bandit assumption is violated, like if you have more of an MDP type structure. How do you do that? These are the questions we're addressing right now. Thanks.
Thank you very much, Susan. Fantastic talk. It's great to see such results and also such introspection about machine learning algorithms these days. The floor is open for questions, or the Zoom, not the floor. Maybe we can, Misha, you can have one more question.
Well, thank you for the opportunity. Actually, I recounted. I think I have 5 actually. So, but
no.
But yeah, I think that my first. I'm a machine learning practitioner, and of course, like my first question is always, can we what was the motivation for using like more, I guess, like complex family of machine learning approaches and methods like reinforcement learning, and of course I understand that there should be some. So I would like if you elaborate it on why. And I suspect that the idea was that the relationship between the user, like their satisfaction with themselves, with their health goals, and sort of that sort of relationship between seeing notifications, interacting with them, and sort of like doing something about their health or not doing. It's kind of a complex, but sometimes even if it's a time series, even there's a lot of noise and a lot of like latent state that we cannot observe. So like, in general, still, like, what was the motivation for using reinforcement learning versus some simpler predictive models, like simpler families? Like in terms of training, because training I believe is hard in RL, like conversions and hard, like a lot of data. You need to have like a lot of data. Your rewards should be somewhat explicit and well modeled. Like it's very sensitive to how you model your reward, and all of these kind of practical things. Like so like they just follow you when you start reinforcement learning. So like what was why?
Yeah. So I view reinforcement learning as continual experimentation, continual learning. That's how I think of reinforcement learning, more in a continual learning setting. And anytime we have a treatment for which there can be iterogenic effects, i.e. burden and I delete the app, or I produce habituation, that's a time in which I need to continually learn. In fact, I'm your statements earlier in the talk were even more convincing for why we want to do experimentation in this setting, because these apps can be incredibly iterogenic. They can be very aggravating. The other thing is we did have a simple version. That was how we got our prior policy. The prior distribution came about by using prior data to form a policy that we could have just straight out used. So we could have said, so the V1 was a complete exploration study. Then we could have gone to V2 and V3 and just done exploitation. I'm glad we didn't already, because already we saw some early indication that the prior policy, that is the work we did, didn't transfer that well. This is not uncommon in health settings, and that's probably because these are inherently non-stationary settings, and the environment. Think about it. Heart steps occurred during COVID, the beginning of COVID. So you have all these shocks that are going on. So my feeling is this is the exact setting in which we want to have a continually learning algorithm. And we're having to learn when to provide decisions. What other method is there besides reinforcement learning? Or actually, you know, we're also involved in control too. I mean, these are reinforcement learning and control, you know, as you know, they're starting to converge, like model predictive control. So there's a whole variety of ways, but this is the way to try. In fact, when my goal is that Kaiser will roll out an app like this, and they should be running an algorithm in the rollout. And then we'll have another algorithm that's monitoring the quality of the app on top of that. It'll be a hierarchical type setup. I wish a lot of these commercial companies were monitoring the quality of their algorithms. Actually, I don't think they're running algorithms. And second of all, if they were, they're not monitoring them, because then they would know that we're all deleting our apps ASAP and we're ignoring all the notifications. Like within 2 weeks, almost all users drop out with these commercial apps. So
maybe I can ask a question, since we're talking about reinforcement. How do you go about choosing the particular states that you are working on?
That's a great question, because the state space is vast. I mean, the amount of sensor data we're getting in. So what we did was we chose them. In Hardships V1, we did a lot of analyses trying to see which states seemed to be important. And then that prompted us to collect new data, new state data in V2 and V3. For example, we didn't collect engagement in V1, and now we are. And but generally where the states came from, where they were expert, the experts told us, these are the states we think, like the expert told us, we think you need to add engagement to your model. Now, some of the features we found in our analysis of V1, like that variance feature that came up in our analysis in V1.
I see. Okay, thank you. Are there other questions? If you have a question, please maybe turn on your video or raise a hand. I would.
Can I ask a question?
Tianxian, yeah, please.
Tianxian.
Hello, Susan. Yeah, this is very interesting. So I wonder, for the 270 days study, since you mentioned that users drop out very fast, how come you're still able to estimate anything for, throughout the study?
Right. So it turns out, okay, we did have some dropout in this. Okay, so the first thing is there were a lot of intervention components in HeartSteps V2 and V3. So the amount of dropout we got was not like you see with the commercial apps. We got much lower levels of dropout than a commercial app, but we still got dropout. And so every user has a different total number of episodes. And so wait, I have to be careful what I mean by dropout. The users are there the whole time. They just stop wearing the tracker. So we're still getting information from the phone. We're just not getting tracker information. Like we got step count from the phone. You get step count both from the phone and the tracker. So the users don't drop out of the study. They just stop paying attention to the app. And that does happen here. And all of these analyses are intention to treat. So they're the worst case scenario. The users who stop paying attention to the app, they contribute a 0 treatment effect.
I see.
Yeah. So these are all worst case type scenarios.
Right, that makes sense. And it makes a lot of sense now that we don't want to send like 0.5 probability notifications when treatment effect is 0.
I think from the reasons we don't want to do that is Misha summarized those reasons very well.
Thank you.
Okay, wonderful. Susan, I would like to thank you once again for taking the time to give this presentation. It was very insightful, very interesting, very exciting. And with this, I'd like to thank you all for attending, and I hope to see you all in the next IACS Distinguished Lecture Series.
Thanks,
Take
Petra.
care. Bye-bye.